This is my favorite class. I'm sorry we've been so technical lately. It's a little bit sad there aren't more people here because this is the best topic of all. But what we're going to do is we're going to polish off our discussion of the interstellar medium and the building blocks that go into the stars. Because when we get back to brass tacks next week, we're going to talk a bit about the life cycle of stars. And what we're going to do in the meantime is take a break and talk a little bit about how our ancestors saw the stars, which I don't think is insignificant. And it's not included in your textbook for whatever reason. In the early part of the textbook last semester, there's some discussion of this. But needless to say, most people on Earth, for as long as there have been humans, have been very, very concerned with what's going on in the sky at night. Very, very concerned, perhaps much more than most people walking around, in Ashland today. And that's kind of interesting. They also had really, really well-formulated ideas about what was happening in the sky, and they're not necessarily the same ideas that we think of today. But the ideas that we've been discussing in this class are very, very, very new, right? Most of the stuff we're talking about in this class has been developed in the last 100 years. Some of it goes back to Galileo, which was what, 300, maybe 400, 3,500 years ago, right? Not even, basically as long as this country's been around, maybe a little bit longer. And that's it. That's as long as we've been thinking about the stars as material bodies in the sky that are living out these, atomistic life cycles. So, okay, the general perspective is that we're super smart now. We figured everything out. We got iPhones. We can Zoom with people around the world. We got everything but flying cars, essentially. So we understand things better than our ancestors. I'm not sure that's entirely a valid perspective. In some sense, yes, we're very technologically adapted and we have material perspectives on the stars that are, in some sense, very compelling. And in other senses, open more questions than we had in the first place. But there's something really, really interesting at the root of the stories that people were telling about the stars because they appear in every culture very, very similarly. And I mean really similarly. Like people are seeing the same animal deities in the sky on different continents who knew nothing about one another, right? The story of the bull, the constellation of the Taurus, the Orion hunter, these things appear in Aboriginal cultures that have no contact with, in Australia, that have no contact with Western civilization. And then people in Mesoamerica, ancient Maya, and the Aztecs, they're coming up with the same stories. And people in Neolithic Europe, they're coming up with the same stories. And so you have to start to ask, what the heck is going on here, right? This is a bit much for a coincidence. And so the story that I want to work towards is that what people are doing is they're reflecting something that's happening inside of themselves in their own social landscapes, and that the way that those dramas play out in our lives turns out to be a very human thing that happens in every single culture. And so when we use the sky as a PowerPoint presentation to relate the drama of our lives, we see very similar patterns appearing because, quite frankly, the cycles of drama that you go through on a daily basis are remarkably similar to the drama that the person sitting next to you is going through. They might have different actors, right? But these patterns emerge, and so I want to drill down into that. And in order to make that case, I'm going to go through a few different cultures from around the world and look at sort of the history of people looking at the stars and what they made of them. But before that, we do need to finish up the last crumbs of the interstellar medium. So let's grab some attendance points really quick. And I'm almost completely through this list now. I have a few more people and then we'll loop back around and do it all over again. So Can somebody, let's see, I will just call on you, remind me of something we talked about last class, and we can review it that way. Oh, we were talking about different ways of keeping time and well, different ways of measuring things, right? We were talking about distance and how people came up with the kilometer, but also how the kilometer and the meter, the length, our standard of length is based on atomic clocks now. And I think my point there was that I was dissatisfied with using the atomic clocks as a standard of measurement because they function differently at different altitudes. And so the conventional explanation, which we will unpack at great length, and I hope that's as exciting for you because the standard interpretation following from relativistic maths is that time itself is slowing down and going faster, right? But you also have to think about these clocks are made out of atoms, right? They're getting yanked on by each other through some sort of mechanism which is a bit inchoate at the moment. And so, of course, the clocks are experiencing the same pressures, right? Of course, a clock that's getting squozen by lots of neighboring atoms is going to behave differently than one that's not. And so these atomic clocks seem to be not very standardized and reliable depending on the location they're at. So I worry about those in terms of defining the meter because it might work here on Earth, but it's not going to work in outer space in so much as you can be in outer space. Cool. Yeah, that is an interesting point. We'll come back. We'll circle back on that. So we actually use this unit parsec too, which is very strange too. This is essentially the distance carved out by one. I believe it's 1 minute. No, it's 1 second of arc, given the parallax base of the Earth in its orbit. So it's how much of that little tiny angle is going to be in terms of distance using the base of our triangle of our orbit, which is very strange. There's a bunch of different distance units that people use interchangeably in astronomy. I apologize on behalf of all of them. I don't know why we don't just call them light years or kilometers or something, but parsecs is what's used often. And so we had to talk about that. Fair, cool. Sorry, remind me your name again? Gracie, I just want to make sure I marked you down. And I did. Okay, then let's finish up. So the first thing that the thing that I kind of stopped on last time was just to review. Look, seeing what's happening in between stars is really difficult, right? Most of the stuff that's out there is invisible, right? We have a lot of neutral hydrogen. We have molecular hydrogen. We'll touch on that briefly, which is just two hydrogens that are stuck together chemically. This stuff is basically invisible. So we have to come up with new means of seeing what's going on, and a lot of it is by looking at the way that light is being diffused or reflected off of these clouds. You're not necessarily going to get nice absorption lines. They're not being ionized, right? They're not giving off their own light. And one of the techniques that we talked about right at the very end was this one, which is the spin flip of the electron, which is a really abstract concept. And I tried to present it to you guys like, hey, look, I don't think that the electron has to be this spooky, mystical, weird thing. You can just think about it as the outer surface of the atom. And it has a polarity to it. It rotates in a particular direction. And so you can think of spin flip as an inversion of that rotation. And this is an interesting physical example of how that happens naturally when something is slightly lopsided, right? And I talked to you guys about this phenomenon and how the Russians were totally freaked out. I forgot to mention they actually made a mini Earth when they were up there in the space station to try this out. And indeed, the mini Earth was doing this spin flip thing too. And they were freaked out. And they sat on this for like 10 years because they were worried that there was going to be mass pandemonium as a result of it. Now, what I didn't, a bunch of scientists came along and they deduced that because the Earth is actually a little bit pancaked, the equator is a little bit wider, let's say, than the longitudinal poles from that measurement, that it was stabilized because its center of mass was at the equator, essentially. Everything's fine. However, one place where this phenomenon might be playing out is the fact that we have these magnetic pole reversals periodically in the Earth. And I wanted to mention this is why I started here, is because we don't totally understand why it is that the entire magnetic field of the Earth periodically, very, very infrequently, something like the last one I think was 700,000 years ago. And they seem to happen every 700,000 years or so. So we're likely going through another one of these reversals right now. Well, I don't know if you guys can go all the way back to when we were talking about how magnetism works. You have these kind of solenoid coil systems set up due to the convection currents in the molten conductive stuff under our feet. Well, there's also the element of if you stick an iron nickel core, something that can be permanently magnetized, it stabilizes and amplifies the magnetic field of a coil system, right? Well, it's thought that that's what's happening at the center of the Earth, is there's this solid iron nickel ball, essentially, right? Now, if that thing has some sort of a handle on it, in other words, if it has some irregularity, some sort of something like this going on with it, it seems like that might provide some sort of mechanism by which it might stably rotate in one direction and then tumble and rotate in the other direction, and we could get a magnetic field reversal. So that solid core is actually bathed in a more liquid-like layer, but nobody really understands. Nobody understands. It's just that it's very difficult to parameterize how viscous that layer, that interface is, and so trying to predict when the thing should change is very difficult to do. Other than just looking at the pattern across history. So anyways, that's another cool example of when you might actually see this kind of strange, anomalous, but regular spin flip behavior that happens in nature. So spin flip's a thing, and it allows us, as a result of it, this gives off a particular type of light when that inversion happens on the hydrogen atom. It's called the 21 centimeter line. And this allowed us to detect this non-ionized hydrogen for the first time, which is when people started realizing, wow, there's a lot of it. Because this is actually the naturally occurring spin flip is really infrequent. I think it takes, a non-ionized atom might spin properly for something on the order of millions of years before it undergoes a spin flip event. And that's one photon that you're going to get out of it. One wave of light radiating. So they realized, wow, the fact that we can detect significant quantities, or I don't know what the right word is, the fact that we see a lot of this 21 centimeter light must mean there's gazillions of these atoms out there in interstellar space that are undergoing this, because it happens so rarely for them that you do the math and you think, wow, there must be a lot of this stuff, right? Okay, there's a couple of other components here. Right around the time, this was maybe only 70-ish years ago after World War II, people began to experiment with X-rays, and they actually got some satellites out into space, and they were able to examine X-ray radiation. So this is really high energy, really short wavelength light, essentially. And they noticed that there was a significant quantity of X-rays that were emanating not from stars themselves, but actually from the spaces in between stars. That was a real shocker, I think, to people, because no one was totally, it wasn't clear how you could get that kind of high energy radiation without a star. The answer they settled on, which is going to play into our discussion next week, is that there's often, but maybe not as often as we wish was the case, stars meet this violent end called a supernova, right? Where they explode violently. And when they explode violently, there's a shock wave, right? And the shock wave actually impacts that interstellar medium. And this excitation is actually what causes those atoms to be vibrated in such a way that they give off this really high energy X-ray light. You know, shock waves are kind of hard to visualize, and I don't think people totally grasp how powerful shock waves in general are, but they're going to play really importantly. They also lead to the generation of cosmic rays, which I'm going to touch on in just a minute as well. Some of the most high energy interactions we have in the universe come from shock waves. So, you know, not to get like entirely graphic here, but when people are in war or something and they experience like explosions from bombs, right? Most people think that people are getting killed by flying pieces of metal and stuff, and that does happen for sure. But the really damaging part about bombs is that they compress the air really fast, and what it does is it squishes your internal organs, right? And so people kind of die from the inside out because of the shock waves. There's so much energy loaded in explosive force as it compresses the air. And obviously, this is a complete tragedy. But it can't be understated how powerful shock waves are. Okay. Now there's one other component we need to talk about, or two actually, molecular clouds. So this was really shocking. People started to realize that they were getting absorption bands as if you put some gas in front of a lamp, you can, like say a star, right, an incandescent lamp that has that nice rainbow, you can see what, atoms or molecules are in the way, right? They screen out, they make these black absorption bands on the frequency spectrum, and you can see what's there. And people started noticing that there was really complex molecules, like big, beefy molecules, like cyanide, just hydrocarbons, very big things that we tend to think of as being a product of Earth chemistry. And this was really shocking to people. They didn't really know how this happened at first. And it turns out, actually some of them are really, really big. There was these things that were huge. These things are called, let's see, what is this thing? This is called a fullerene. Huge cage-like configuration of carbon, right? Very, very, very complex structures. And people were trying to figure out how in the world this happened. Water was found, ammonia, carbon monoxide, things like this. What was going on? Well, it turns out that those pieces of dust, which are in some sense left over from blown up stars and from condensation reactions that happen, right? We talked about the fog last week, right? And how that's essentially a cooling reaction where the water comes out of its gas phase and links up with other waters, and you get little droplets, actually, right? This is a condensation reaction. It's cooling, right? It's thermodynamically favorable. It's a relaxation reaction. Well, this same thing can lead to the production of complex molecules as well. For instance, as these carbons cool, let's say they're blown off from a star that's exploded, as they cool, they actually settle in just like ice into these very nice geometric patterns with one another. Well, as the dust grains form from these condensation reactions and from the little bits of blown up stars, what they do is they have these little caves and crannies on these dust particles, and they shelter all the other molecules that happen, or the other atoms that happen to fall into these places, and they act like little hands to squish them together, almost enzymatically, like you would expect inside of a piece of biology or something. So you have these little sheltered caverns inside of the dust where light can't get in, right? Where nothing, high energy rays can't destroy them. And you actually start to get the assemblage of pretty large molecules as a result of it. So there's big things being built out there. And a lot of those big things help us understand, in some sense, how our planets could be formed as a result of it. It's very difficult. There's huge problems in planetary science, which we talked on last semester, which come down to how do you get little pieces of dust to turn into a boulder, right? It's very difficult to do with gravity alone. But if you start thinking about all of these complex molecules that are starting to be assembled, they're pretty heavy. They start to actually stick together through chemical means as well, through electrostatics, through electromagnetics as well. You can actually build some pretty big building blocks up over, huge stretches of time. And so these are the really big Legos that we're going to be using to build stars later, because what we need to do is get a bunch of stuff in one place. And if everything's just an ionized gas, or everything is just a bunch of individual atoms floating around, it's very difficult to concentrate them, gravity being so weak of a force. All right, so how do we see these dusty clouds? Well, one of the ways we see them is they basically make these holes appear in the night sky. It looks like a hole, but in reality what it is it's just that you're screening out the light from the stars behind them, right? It kind of looks like a big ghost or something. Another way is that we get these cool halos around stars, right? These big cloudy regions around them, which is actually the light being diffused, scattered off of these big dusty clouds, right? You've probably seen this when you walk into a room, like an attic, and it's really dusty. you blow off an old book cover or something like that. Another thing that we see is this idea called extinction, which is where the blue light is preferentially scattered off of these clouds. And the result is that the red light, the longer wavelength light, is what makes it through to us. And this is a different concept than redshift, which is going to matter a lot when we get to cosmology. And we've been talking about this Doppler shift on the technical side of things the last few classes. This is a different matter. So when you have Doppler shifts, when you have red shifts, you're talking about all of the lines in the frequency spectrum being shifted towards the red. In this case, we're just talking about screening out all of the light other than the red. And so things can appear redder, but the spectrum itself doesn't shift. So that's another way of evidencing interstellar dust, which turns out to be a huge player in this whole process. So here's an idea of that. You see the blue ones are getting preferentially scattered off. Now, this actually opens a whole can of worms, which I'm going to probably pass on for now, but I'll come back to. But in general, big wavelengths of light have an easier time penetrating and getting around smaller barriers, right? Now, big wavelengths can have a hard time with big barriers, right? So radio waves on Earth, I don't know if you guys have ever gone, probably. We live in all these valleys here, right? You can easily go into a valley that has it's radio dead, essentially, right? Those waves can't penetrate through the mountains or whatever you want to call these things around here. The higher wavelengths they can rattle around in there and scatter, and you might actually, if you had very high radiation, you might be able to, a high wavelength radiation, you could probably see it. But you don't get very good radio signals, right? So, and you can actually use that effectively. You can bounce radio signals off of things, that works. But these long redder is closer to the radio side, longer wavelengths, they tend to have no problem with these dusty regions for whatever reason. And we can talk about why that is, but I don't want to go into the details right now. We'll probably come back to it. There's some atomics to it, but I want to get to the ancestors as soon as possible here. All right, so I don't know that we need to go too much deeper. We do need to touch on cosmic rays. So cosmic rays are one other thing that we're going to encounter. Very, very strange. So a cosmic ray is not actually a piece of light, despite the name. It's named that way because they're very, very high energy and they seem to travel in a straight line, rectilinearly like light. But in reality, cosmic rays are just atoms that are flying really, really fast, like almost at the speed of light, ionized, right, charged, moving really, really fast. And people spent a long time after they discovered these in 1911. This guy was flying these instruments, I think in balloons, up very close to the edge of the Earth's atmosphere. He was discovering these incoming collisions with these particles. It took people a long time to figure out where they were coming from because, unlike light, which travels in this perfect rectilinear fashion, these charged atoms actually are subject to magnetic perturbance, right? So any time that you have a charged atom, it will be deflected by a magnet, right? And there turns out to be all sorts of magnetism going on with these stars, as we've seen with our own sun. But there's even bigger magnetic contributions. The galaxy itself has a magnetic field, right? So you can imagine that magnetism is really, really a powerful actor, especially on really lightweight things like individual atoms. And so people have been still to this day trying to make sense of these cosmic rays, where they're coming from. The best theory right now is that similar to these shock waves exciting the interstellar gas and making these X-rays appear, right? Getting this really high intensity radiation to be emitted from these gases. Similar to that, what happens is in the shock wave, there's actually atoms that are being reflected back and forth along the front of the shock wave. And what happens is that they will spend a very long time, I think on the order of 1 million years sometimes, in these supersonic shock waves just reflecting along the front. And at some point, there's quite a bit of magnetic turbulence there as well, just like at the surface of the sun, and they get accelerated, and at some point, a few of these atoms will get kicked out of the shock wave, and they are traveling at these really, really high speeds. That's the best theory for cosmic rays that we have right now. It's maybe maybe a little bit less than satisfying, but that's the best that people can come up with. Now, the question is, like, how much do cosmic rays affect us here on Earth? The good news is that we have that nice magnetic field, right? This is a huge reason why these, because otherwise, look, if you just, it's a huge problem actually, if you go outside of our magnetic field, which is generally considered beyond this thing called the Van Allen radiation belt, it's really dangerous to be out there actually, because of things like cosmic rays. What happens when an atom that's going almost at the speed of light crashes into you? You might think, well, it's just an atom, like how much damage can it do? And it's like, well, the damage it does is that it can change the structure of your body at the molecular level, right? So it can not just break you apart, but it can actually change your DNA in a way that makes it not functional for you in the future, right? So cancer is a really huge issue. Immunological dysfunction, right? Your immune cells getting rewired to not do their job anymore. These are huge problems for astronauts that are planning to, make those big space flights to the moon and to Mars, right? Especially Mars, because that's going to take, I don't know, half a year to get there. That's a long time to be hanging out without a nice magnetic field around you. So people are trying to figure out different ways of shielding these spacecraft and everything. And the question becomes, sometimes, so these cosmic rays do make it into the lower, or the upper atmosphere. They penetrate sort of not too deep into our atmosphere, but some of them do make it down. And they may have a role in changing the way that our clouds are structured here on Earth. So there's a really interesting scientist, this guy named NearShiv, who's in Israel. He's got this cool theory that what happens is, as the Earth is making the sun, all of us, all of our planets are making their way through the Milky Way. Remember, the solar system's also orbiting the center of the Milky Way. That means it spends time in the really thick arms of the galaxy, and it spends time in the really empty, dense regions of the galaxy. Because the galaxies, we haven't talked about galaxies too much yet, but they're basically these at least ours is this pinwheel structure, right? It has these regular intervals of density and sparsity. Well, his idea was that a lot of the cyclic changes in our climate across the eons could come down to the way that cosmic rays become more of a problem when you're in those dense regions of the galaxy. I think it takes something like 200 plus million years for the solar system to make an entire transit of the galaxy. And of course, we've done this many, many times in the life of our planet. Even since life itself has been here, that's happened many, many times. And the question is, when it goes through those dense regions and we're getting all of these cosmic rays, might they have a role in actually seeding clouds on Earth in some sense, right? Actually breaking apart, giving, let's say, energy to the water in such a way that it results in more collisions with itself and has these condensation reactions, that it actually nucleates more weather in some sense here on Earth. And so he's kind of devoted his career to providing different models for how that might actually happen. And it's, far from a very, I wouldn't say this is a consensus idea at all, but it is very intriguing. Okay, so let's review this. This will be, let's put a bow on the interstellar medium. Does anybody have any questions about interstellar space before I move on from this, first of all? We good? All right, let's just review this a little bit. So, I think this is actually a better way of looking at it. As the stars mature, and we'll talk about this maturation process very soon, they begin to lose some of their newly made elements, right? And this is already happening with our own star. We have this stellar wind, right? There's this almost evaporative process, and the magnetic tangles end up flinging a lot of this material, these atoms, off into interstellar space. So there's this reservoir of interstellar material that's being constantly kicked out by each one of the stars. And sometimes when stars die, they contribute much bigger pieces of material, right? there's some huge stars are definitely synthesizing big elements. They're fusing huge things, right? But even the little stars are constantly, they're like vacuum cleaners. They're constantly sucking up all the big heavy stuff from the solar system. There's constantly huge iron meteors crashing into our sun with huge heavy elements in it oftentimes. Not a lot, but a little bit. But you got to think, over the lifetime of a star, it's swallowing up tons of stuff, right? So even a little star like ours that only really fuses hydrogen and really mostly can only make heavy hydrogen and helium, it's also going to, by the end of its life, have a lot of heavy stuff. Iron, carbons, all of these things, right? And so those are going to be kicked out when the stars die. And dust grains can form as these things condense, and the dust grains shelter more reactions. And you have the interaction of the dynamics from these exploding stars that are in some ways exciting all of the atoms inside of this space. And you really have a very frenetic environment that has really active regions on the outside of these clouds, but you also have these cool sheltered regions where ice crystals can form. You have the grains themselves that are, in some sense, shielding all of this radiation so that more complex chemicals can develop. And in the end, most of this stuff is going to go back into the creation of new stars, and we're going to see how that happens next week. So that tees us up for understanding the birth of stars, which will tee us up for understanding the death of stars. And all of this is going to go into the construction of galaxies eventually. And once we understand galaxies, then we're going to start talking about the wider landscape of galaxies and how they're interacting, because it turns out that galaxies are not just evenly distributed throughout the universe, right? They tend to be organized into these very spiderweb-like filaments of galaxies. The universe itself seems to have a really interesting structure to it. So we're working towards that. And what I want to do now is take a little bit of a break from this, and I want to motivate our quest for understanding this a little bit. And in some sense, I know we've been going really hard into the technical details for the last few lectures. So with the back half of this class, I want to pause and ask everybody to consider how long this human project has been going on, first of all. And what I mean is, anthropologists have this idea of behavioral modernity, right? When humans, not necessarily when our skeletons looked like humans, but when we started acting like humans. When was that? And what does it mean to act like a human too? Well, there's a lot of arguments about that, but it seems to have been going on for a really long time, like tens and tens of thousands of years at the minimum. Although I saw a really, and you can argue about what it means to be a human, first of all. It's like, well, we seem to have some propensity towards technological innovation, right? We make tools. Now, some other animals make tools to some extent. There's these monkeys that'll fish ants and termites out of the ground with these sticks and so forth. But they're not constructing intricate houses and so forth. And there's some birds that construct intricate houses, but they're not using tools. And so there's this convergence. There's something to that. I think there's something more about humans, though, that involves the acquisition of symbolic language, though. And I think this is what people mostly mean when they talk about behavioral modernity with humans, is that we've found the ability to not only give names to actors, right? And I think that's one of the most primitive things. So if you take a bunch of chimps in a cage and you throw a fake snake down on the ground, right? They'll actually make a sound that is in some ways symbolic of that snake being in the room. And they'll do it. They all kind of know how to do that without having been taught, it seems like. And they all know what the other one says, right? And they'll all be very freaked out at first. Everybody will come running and and then at some point they'll realize it's a fake snake and they'll start playing with it and everything. But so there's some symbolic representation of, say, an object that seems to be very primitive. But humans developed this very bizarre ability to link these different objects, these material actors, together and make abstractions out of them, and then to represent those abstractions with sounds coming out of our heads, which is really, really weird. And nobody else seems to be able to do it to the degree that we are. there's some evidence that there is abstract communication through language and things in some species, like whales that come to mind. But nobody's decoded that enough to really put a definitive, let's say, representation of what each one of these sounds means, or whether they're just in some sense tribal identifications. Like, we have this song, if you can sing this song, you're part of our group now. Okay, that's cool, but that's not exactly the same as an abstract representation with sound. And at some points, anyways, it seems like maybe somewhere between 50 and 150,000 years ago, people figured out how to do this for the first time. Now, one of the first things that comes along with this is at least what I'm going to hypothesize, is that the fundamental unit of transmission of knowledge, the story, is born for the first time, right? Now, you have a really hard time actually conveying anything to anybody without telling a story of it. I've seen people try to. Sometimes you get in a conversation with someone and they just start unloading facts on you, right? And you're like, at some point, you're just like, what are you talking about? What is happening here, right? Stories have beginnings, middles, and ends to them, right? There's an arc to a story. And this is just, for whatever reason, this is the easiest way for humans to remember something. So if I tell you a story, let's say, if I'm trying to explain the interstellar medium to you and I don't tell you, the beginning of it, where it comes from, or let's say, about stars in general. The whole point of this course, in some sense, is to tell the story of a star from the beginning to the end and how they collaborate, and maybe even give us a story of the universe at the end of the day as we build it up from stars. But I can't just tell you everything I know about stars with no relation to one another. I have to articulate these in a very concerted sequence where I start with the pieces of the star. And I tell you what a star is, first of all. Then I tell you how the building blocks of a star, how they can assemble into a star, and how they can come apart, right? There's a whole arc to this, right? And we're all very familiar with it. I think it's very easy to understand this because a human being has a beginning, middle, and end to it, right? And this is completely obvious to the earliest ancestors as well. And I think they became very concerned with this story. And in particular, I think they became very concerned with the ending of the story, right? Now, most animals don't seem to have much of a recognition of the fact that their lives are going to end someday. They have some instinctual avoidance of bad things that might happen. But there's only a few species that actually seem to mourn their dead in any way, and I think elephants are on that list. There may be some others, but it seems very rare that creatures have this recognition that, well, that thing that just died over there, that's going to happen to me someday. I think this is one of the first abstractions that humans made, was actually this. And it turns out to be probably the most disturbing thing that anyone will ever realize in their lifetime, is that everything they're working towards will disappear one day. So I think there arose a very real need in the stories that people were telling themselves about the universe around them that protected them against that very, very disturbing ending to the human story. Now, I don't mean to pathologize them and say that's just a defense mechanism or anything. I mean, it's a real crisis that people have to make sense of. And so what happened was, for most of human history, by the way, right around the same time, it seems like people found and figured out how to cultivate fire and move it around, maybe 50 to 150,000 years ago. They were actually probably building these campfires. They had this whole landscape of stars above them. They didn't have these fluorescent lights. They didn't have PowerPoint presentations. They didn't have Netflix. They didn't have anything. It didn't even seem like they had theater or drama, really, to act these things out. But I guarantee you they had stories, right? And they had this incredible tapestry above their heads in which to use as a visual aid to tell these stories. And that's what's really interesting about studying the myths that people have told, of course, thousands of years about these stars, is because I think they can tell us a little bit about these people and about ourselves, because ultimately, anatomically, physiologically, we're basically the same thing. We haven't changed that much genetically in those 100,000 years. We're essentially the same hardware, right? So we're still obsessed with explaining a lot of the same crises to ourselves. And that is why I think it's really important for us to look at the stories that these people are telling. Excuse me. All right, so taking that idea of the story as the basic unit of information transmission, I want to work towards looking at one particular myth, which I think resonates all throughout history on all the different continents. Now, I think we talked last semester about, let's see, what did we talk about? We talked about the bears, the Ursa Major constellations. Today I want to talk about Andromeda. Okay, so Andromeda is this, well, we'll get to Andromeda's myth in a minute. But needless to say, people didn't realize Andromeda was a galaxy when they were telling these stories. It was just this little cloud, this little cloudy star-like thing in the sky. It's treated as a nebula. Now, of course, we understand that constellation represents a galaxy, which is, of course, basically a whole other universe, right? It's hard to imagine trillions of different stars in this galaxy that we would ever even have time to explore it, and then that there's just trillions of other galaxies out there just like this. The scale is just unimaginable. So this whole other world is what they ended up talking about. But what they did with Andromeda is many cultures told this story of a dragon, right? And this beast that was tormenting the city and so forth. And it turns out that the myth of the dragon is so ubiquitous, it is unbelievably conserved across cultures that it's worth us picking apart for a second and trying to understand what the heck people are talking about. Because, of course, you might think to yourself with your modern scientific mind, I've never seen a dragon before. Who cares, right? But maybe you have, so we'll talk about that. All right, let's go all the way back to the beginning of the record. So what we have here is a piece of a mammoth tusk that was carved up with a figurine and a bunch of little tick marks on the back of it. This is perhaps the oldest piece of astronomical record that we have. This thing is 32,000 years old. So this is before the last glaciation. And actually, people discovered this thing a long time ago, and they thought, that's kind of cool. It's a nice little figure, these like primitive people who are carving. And this astronomer came along many years later and was looking at this, and he was like, it's kind of hard to see here, but there's some tick marks across the belt of this gentleman, and he started aligning it, and he found that this looks a lot like Orion, actually, the constellation Orion, but not quite. Well, what he did was he back calculated it to the age that they had carbon dated this sample to, and found that where the stars were projected to have been at that point in time matched identically to the points on this figurine, which of course we can't see as perfectly as I would hope we would. On the reverse side, there was all these tick marks, and it turns out that the tick marks, let's see, there was actually 86 notches on the back of it. Well, it turns out this is actually the number of days at that point in time that Orion's two prominent stars, one of Orion's most prominent stars, Betelgeuse, which is kind of this pulsating star that we can see right now. It actually varies from day to day here. This is the number of days that it was visible above the horizon. It's also the average number of days of a pregnancy, which is really quite interesting. So they might have been trying to relate something about their own experience to the stars as well, which is quite fascinating. Of course, that's all we have. We don't have the accompanying textbook or whatever the heck the stories were these people were telling. But there is some evidence that people were taking the stars very seriously at that point in time, and perhaps trying to connect it to what was happening here on Earth. There's also this other cave painting. This is from about 17,000 years ago. This is found in a cave in France. This one's really fascinating. It was actually the same astronomer. So again, they discovered this thing a while ago. This astronomer, let's get his name. I feel bad not naming this guy. His name was Michael Rappenglueck. Okay, Michael found that these dots actually, again, coincided with the exact location of those stars at that point in time when you do the projections backwards. And so what's really interesting is that this constellation in particular, the Hunter Orion hunting the bull, the Taurus, that one appears all over the world, over and over and over and over again. And you might think, why in the world is that? Why are people telling this exact same story? And it's like, well, there's something about that experience that must go beyond the fact that we're just shooting these things and eating them for meat, right? There's something that people are recognizing about this process. First of all, hunting animals with a bow and arrow. Anybody ever done it? A little bit? How is it? It's hard. It's really, 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 really hard, okay? And it's also really dangerous, too. So now, you probably are using a compound bow or something like that, right? So compound bows are wonderful. You pull them back. You can sit there all day. They have this gearing system where you can just sit there and wait for your perfect shot. They have perfect sighting and all these. These people were forging these bows out of wood, right, with sinew strings. And you can't, these people it must have been an obsession. Like the way that people practice, maybe kids, when you were growing up, you played basketball or something, people would just practice and practice. Or if you played sports, maybe you played a musical instrument, you practice these things like 4 or 5 hours a day. I think that's what people were doing with bows and arrows back then, for sure, right? So this process, and I'm sure a huge part of becoming a functional member of that society, particularly for young men, was getting really good at this, right? This was a central piece of your identity in terms of being a useful component of the group, right? And so there must have been incredible stories that motivated people in order to see their place in all of this, right? It must have appeared as such a central part of being a young person transitioning to being an adult that, well, everybody must be doing it. The gods themselves, the stars must be going through the same process as well, right? Look, we can look in the sky, we see this happening. This is a universal. This is something that we can all relate to. And so no one really knows the particulars of this process, but there persists in these isolated indigenous communities, like the Aboriginal communities in Australia. There are these really, really rugged, trials that the young people have to go through in order to become adults in this society. And they often involve being able to join the group and go and partake in the hunting ceremony as a result of that. So it's a very central aspect of their lives. It's the central drama. This is their ESPN. This is their, Olympic sports. This is their graduating from high school. This is like everything rolled into one. And this story seems to have persisted across multiple cultures, and people have all been very, very much obsessed with seeing similar things as a result of it in the sky above them. We'll skip this one. All right, so, let's talk about it. So this is an artifact, another piece of bone that was carved. This is from 35,000 BC. This seems to have marked out the moon's phases on it, which is interesting. So it seems like people were, in addition to telling stories in the sky, it seems like they were very interested in tracking the time of how things went down. Now, I don't know if I mentioned it in this class, but it's rather uncanny that, of course, the moon has an orbital period of about 29 and a half days, which is almost identical to the minute with the average menstruation cycle for a woman, so the fertility cycle of human beings, right? Now, it really makes you wonder if people were able to clock their fertility cycles by the moon, and that was one of the first motivating factors in keeping track of the motion of the moon throughout the sky. Humans are actually really weird primates. We're the only primates that, we're weird for lots of reasons, but when it comes to fertility, it's very strange. So most primates, when the women are fertile, it's really obvious. Their bodies change radically at different points in their menstruation cycle, right? Human beings, not so much. It's actually very difficult to tell when a woman is ovulating unless you know her really, really well, right? It's very, very difficult to see. So I wonder, and this is just pure speculation, how much, and others have speculated this as well, how much humans were actually using the phases of the moon to time their fertility cycles, right? Because, in some circumstances they're very interested in making more children, and in some circumstances they're not. And you can actually work around that if you want to, right? You don't actually need, God, this might get me fired or something, but you don't really need birth control to not have babies, right? You need to just really plan your activities appropriately. So, were people doing that? I don't know. They seem to have been obsessed with it. Now later on, this is a picture, a schematic of this site that was found in Scotland, ancient Scotland. This is from about 5,000 years ago. People began to become really obsessed with trying to make the moon, the lunar calendar, right, this 29.5-day cycle, line up with the solar cycle, which is of course a year long. They didn't line up very well, right? You can't quite squeeze an exact discrete number of months into a year, right? And so people were trying on all sorts of different ways of figuring out how many years you would have to go through in order to have it line up again. And there was some different tablets. I don't understand the inner mechanics of this, but the claim made by the archaeologists is that that's what these individuals were doing. They were marking the phases of the moon, where the sun was rising on a given particular, or on the solstice, or an equinox. And they were correlating those in such a way that based on the year, they could keep track of how many moons had gone by, and they were trying to, in some sense, analyze and decide how many moons exactly went into a year. And that's what they're trying to keep track of. The same thing goes for this bronze disc that was found. This is from about 1600 BC. They were still kind of hammering this out, trying to figure out how many moons fit into a year. I guess, again, I don't know the details of how the theory goes that they figured that out and marked this in this disc. But needless to say, it wasn't until the Romans that people really, that was when we got the Julian calendar set up. And we talked about this last semester a lot more. But it took a really long time for us to get a calendar that was stable. And even the Julian calendar was shifting, right? It was, at some point, the winter solstice was happening in March. And I believe Pope Gregory, was it? Set up this Gregorian calendar where he basically moved the days back, deleted a bunch of days from the year, and added this thing called the leap year in, which took care of that problem for us. So this problem of how to time things, right, and how to sync up the moon cycles with the sun cycles and really figure out some regularity becomes an increasingly persistent objective for people as they look up at the sky. But it doesn't stop them from considering the stories that go along with them at the same time. And what's really interesting is that today we're really, really concerned with the mechanics, right? We have, as you've noticed, we have these very, very intricate, detailed models of the clocks, let's say, the mathematical relationships of the stars to one another and the atomic processes that are going into them. But we've in some sense abandoned the stories that are being told across them at the same time. Now that makes sense to some extent because we have movies and music and all of these things. I think music was probably a really intricate part of that campfire situation as well. Actually, some of the oldest artifacts that we found from prehistoric peoples are flutes. You see them all over the place. So people seem to have been really into music, which probably went really nicely with stories about the sky, and maybe even songs about the stories that were happening in the sky. Okay. I'm going to blow through some of this. Okay, so modern astronomy seems to have taken its roots in the West, at least, in Sumeria, and Babylon, which is an interesting place. Does anybody know where this place is, where Babylon is located at today? Yeah, it's in Iraq, right? It's really quite tragic, actually, because it's the cradle of civilization is what they used to call it anyways. Of course, there's civilization cradles in the Indus Valley and in China, ancient China as well, in the Americas as well, much later. But yeah, the cradle of civilization is essentially a destroyed rubble heap now, thanks to this nice military project that's been going down for most of my lifetime, which is really tragic. But and you see pictures of Iraq too, even from the 50s or something before it was utterly decimated, and it's pretty dry and deserty there, right? It doesn't look like the kind of place where you'd want to set up shop for the first civilization. But it was a very different world back then. So this civilization emerged, let's say, maybe 4,000 BC, so 6,000 years ago. Well, 6,000 years ago, the Earth was coming off of this glacial period. The glaciers were melting, the seas were rising. There was probably tons of rain for the first time as all of this water made its way down into the lower latitudes. It was a very green and beautiful place 6,000 years ago, and that's really hard for us to imagine when we think about the Middle East being this effluvial, wet plains of fertile bounty and so forth. Now, it's very hard to trace exactly where these people came from. So the Sumerians are really, really fascinating because they have a language which is distinct unto themselves. In other words, it's an isolate. It doesn't seem to come from any other language. And we can trace the language that I'm speaking to you right now all the way back to these Proto-Indo-European ancestors, right? And the roots of that language are shared with people in India. They're shared with people all throughout the Middle East and the Mediterranean and all the way up into Northern Europe and parts of Russia, the steppe, right? We can trace all that back, but for whatever reason, the Sumerian language doesn't trace back to anywhere, which is really, really weird. There's a couple of those. The Basque people in Spain, on the boundary of Spain and France, also have a language isolate, which nobody's been able to connect to anything else. And there's a few of these around the world, which point to some sort of history that we're missing, right? Now, there was some hints of towns and cities that were occurring in modern-day Turkey, which were very different. They didn't seem to have central leadership in the same way. They were almost like these big apartment building complexes. They didn't really even seem to have a central religion of any sort. People like to point at these, and I'm thinking of a site called Çatalhöyük, and I'm thinking people like to point at these as some sort of utopian fantasy, like these people were all egalitarian. All the houses are about the same size. There's no palace or anything, which is very bizarre. And I don't know how much truth there is to that, but that wasn't the case in Sumeria. So about that happens maybe 10,000 BC, right after the last glaciers start to melt. Then silence for like 3,000 years. Nothing happens. No cities that we can find. And then all of a sudden, we see Sumeria appear in the region, like a bit further south, down on the Persian Gulf there, right? And Sumeria is a very hierarchically structured civilization, right? There's class structure, there's kings, there's nobles. They have a very well-defined religion that reflects their own social organization very much. There's supreme deities that rule over other deities, and it's this very, very well-fashioned edifice. So I probably should have showed this to you earlier. This is just a good picture of where I'm talking about, which is down there on the Persian Gulf in modern-day Iraq. So what's really interesting about the Sumerians is that, we still live. Our astronomy is built completely on the backs of the Sumerians, right? So, the fact that the clock is divided into 60 minutes, right? That's pretty, I don't know if any of you have ever thought about that before, how bizarre that is, right? When everything else in the world is divided by tens, right? Why in the world did we divide the clock into 60 minutes? Well, we can thank the Sumerians for that, and the Babylonians in particular, or slightly downstream of the Sumerians. And they counted in groups of sixes, which is very, very interesting, right? And you might think, why in the world would you count in groups of six? So 10 makes a lot of sense, right? You got 10 fingers. So, I've never had a hard time comprehending that. 6 is a little bit trickier, and I've heard some proposals, but I would invite you guys to think about that one over the weekend, and tell me next time if you have any ideas for why in the world the Babylonians chose groups of 6. The best one I've heard is that we have 3, what do you call these things? Chunks of finger? I don't know, what are they called? Digits, maybe? No, interdigits, maybe. Anyways, you have 3 little flat pieces in each one of your fingers. And so you might be able to make up groups of 3, and you can make up groups of 6 this way. Ultimately, you could make, 15 on each hand. I don't know, it strains the imagination. So I'm curious if anybody has any reason why that persists. But at any rate, look, we divide the sky into 360 degrees, which is of course multiples of 6 and 60. And even our definition that we belabored about the parsec comes down to essentially a Sumerian definition of how to chop up space, right? So we can't get away from that, and it's really interesting. And these people also did something which was very bizarre. They started to specialize their civilization to a degree that really only seems to be rivaled in modernity. So if you think about it now, we have a group of people that do all of our astronomy, right? I mean, there's some amateur people who like to look at telescopes. Maybe you even own a telescope. But for the most part, it's these professional people who are the ones staring at the sky telling us what's going on. The Sumerians had those people too. They were actually an ethnically distinct group of people called the Chaldeans, and they lived in a special part of town. They had their own neighborhood, right? So that's very unique. It's almost like, in some sense, it kind of reminds me of a university like this, where people are getting together, except these were just the astronomers. Now, astronomy and astrology were completely fused at the time. So that's really interesting, right? The astronomers, the people who are watching the motion of the stars in order to plan the harvests and plan and make calendars and technologically apply what they're learning about the motion of the earth, those same people were in charge of relating and divining the stories that were coming down from the sky, right? And so they were in some sense the myth makers as well. And this will all become very apparent soon. So the Chaldeans, right? Now this is almost like as if you had a place in New York City where all of the astronomers for the United States lived. It's very hard to imagine this being the case. But I think that it shows you just how important a piece of this world it was for these people. Now, what's also interesting is it doesn't seem like they treated the Chaldeans very well. That's really interesting, right? You know, and in some sense, I could imagine people saying something similar about us maybe someday as well, right? I mean, if you think about who in our civilization are the people that we give all of the wealth to, it's like sports heroes, rock stars, and like stockbrokers, right? And like, I think that those things would have seemed absurd to some other civilization at different points in time, right? Like, why would you give the guys who are just helping you manage your money all of the money? Why would you do that, right? And that's a really good question, by the way, which our entire future may hinge on that question. But it's a good question, right? In some sense, you know, I can understand the athletes and the rock stars to some extent. These are people who have, you know, in some sense, they're at the extreme ability level in their particular domain. And so rewarding people at the extreme meritocratically makes a lot of sense, I guess. But we don't really give a lot of money to astronomers these days, and or academics in general. Not to cry you a river, but it's very difficult, right, for people to be full-time academics in this world today. And I think it was a very similar situation back there in Sumeria as well. So maybe a prestigious situation. There's an argument to be made that, you know, the way that we call academics doctor, right, or even physicians doctor, is maybe the last vestige of a feudal title that remains, right? So in feudal times, you would call people like lord or sir or something like this, right? And it's almost like doctor is like the last bit of that remains, essentially. So there may be some prestige associated with it for the Chaldeans, but they certainly weren't wealthy people, although they were absolutely essential to the ongoings of the Sumerian people. Okay, so the same thing was kind of happening over in India. We have an even worse record, unfortunately, of the Indus Valley civilization, which is why I'm not able to speak to it as deeply. The script from the Indus Valley civilization still hasn't been broken. So if anybody wants a really difficult project to accomplish in your lifetime, go crack the Indus Valley script. You will be famous for all of time, and the world will thank you for it. So we don't know as much about them. They do seem to have been obsessed with the stars as well, and predicting the solar and lunar eclipses, the different alignment of the sun and moon, and so forth. And of course, the stories that they're telling in the sky, very similar to the ones that the Sumerians are telling, very similar to the ones that the ancient Chinese are telling, very similar to the ones that the Proto-Indo-Europeans, the Neolithic Europeans were telling. You just can't get away from some of these stories. And I want to save time to go over one of them for you, so I want to make sure I get to that. Obviously, the same thing is happening in Egypt. The pyramids were aligned to the pole star at the time. Does everybody know what a pole star is? We talked about it last semester. But yeah, it's the star that doesn't move. Now, it doesn't move because, well, it's at the North Pole, and everything, the whole Earth is kind of spinning around, right? And so it stays put. So if you actually take a time lapse of the night sky at any given point in time, and you focus on the North Star, you'll see all the other stars just spinning like a wheel around it, right? Now, for whatever reason, the North Star changes from epoch to epoch. It moves a little bit through this process which we call precession. So they had a different North Star in the time of the Egyptians. And it took people a while to figure this out. There's an argument that the Egyptians were also aligning some of these structures. They were very obsessed with Sirius, which is one of the brightest stars in the sky, the dog star. There's some arguments being made from time to time that the pyramids are actually in some sense reflecting Orion's belt on the ground as well, that they can be projected onto the sky in that manner. So of course, I don't have time to go into all the details, but the Egyptians were very much concerned with the sky. Their mythology reflected it. Ancient China also, it actually seems like the ancient Chinese astronomers were some of the first people to actually record a supernova, which is pretty cool. They also were the first people to notice variable stars, which is really interesting. We talked about variable stars in terms of getting the timing and using these as standard candles. This was, 2,000 years ago. These astronomers with no telescopes were actually able to see the variation of the brightness of these stars. And they called these things, what did they call these? Sorry, they didn't have a name of that. For the supernova, they called them guest stars because they would be there and then they would disappear, just like someone visiting your house. The Mayans were very, very interested in the stars. They were mostly interested in Venus, which is really strange. Nobody else seems to have been quite as obsessed with Venus. The Sumerians were pretty obsessed with Venus, to be fair. And they told this story that I don't have time to get into. I went into more last semester about this descent into the underworld, right? Which is a very archetypical human experience. I'm sure we've all had it, whenever I talk to somebody, I'm like, how's it going? Well, what am I asking? I'm kind of asking, like, how's your journey through the underworld going? Are you coming back up or are you going down, right? Everybody's going through this constantly, You reach these really dark places where, like, nothing's working out. Maybe your significant other just broke up with you. Maybe you had a fight with a friend. Like, maybe you lost your job. Maybe you didn't get the grade on the exam you wanted. Bad things happen, right? But as a result of them, we rebuild ourselves and we claw our way out of that underworld. And Venus does this same thing in the sky, right? Venus, as it makes its way around the sun, it actually goes behind the sun for a few days. And the ancients would interpret this as it would spend, most of a year on one side of the sun, which would appear to them in the morning, right, in the east. And then it would disappear for a few days. And then it would spend the rest of the better half of a year in the evening, right? So they saw this journey that we're all going through on a regular daily basis playing out in the drama of Venus. And that story appears over and over and over again. All right. I'm going to run out of time here. Let me see what I actually want to get to. All right. It's quite interesting. I think what we're going to have to do is we're going to have to continue this next time because I'm not willing to give this up. So something really interesting happened. The astronomers and the astrologers, the myth makers, the people that we would say today are the religious sects of society, they were one and the same for almost all of human history. Actually, all the way up until Galileo's day in the 1600s, this notion of the stars being under control of the deities was very much the dominant theme. There's also no real separation of church and state for any of these civilizations until very, very recent. That's a completely modern idea that you shouldn't involve religion inside of your state. And that's come with its own set of problems as a result of it. Galileo famously was one of the first people to challenge this. I think Giordano Bruno also was one of these people, although he was somewhat less successful. He ended up getting, he had the postulate that, hey, I think that all of these stars might have planets around them and they might have people. And the Pope didn't like that at all, because people are supposed to be the special ones. And they burned him at a stake in front of an audience of 300,000 people, right? So everybody was into it. They thought that's a really good idea. You should definitely burn people who have ideas like that, right? And you think that, that we're completely beyond this, and of course we're not burning people at the stake, but there's a very much a strong tendency in our modern civilization to excommunicate people and to want to cancel people whose ideas you don't like too much. And I think this is the remnant of a very old way of being, where people are very much trying to protect the superstructures of their civilization, which isn't entirely an unreasonable thing to do, right? So you have to ask, what the heck is going on? What does this word religion even mean? Like, what's going on? And I think that if you actually tear the word religion apart, you'll find that the word religion actually, religios from Latin, actually has to do with this idea of binding, right? It's like this glue that holds things together. So when you think about what a law is, and you think about what a religion is, well, what is a religion? Let's pick on the Bible for a second. It has, the first part of the Bible especially, it has this code of conduct, essentially, right? These commandments of how you're supposed to behave. It's really not that different from a law. It's essentially an ethical framework for behavior, which, interestingly enough, the same basic ethical work appears in civilization after civilization, right? It's not like the Bible was the first place that said, hey, you shouldn't steal from people, right? Everybody figured that out. They'd even put it in writing. The Sumerians had their own version of that, which they etched on these giant stela, which they would place in the center of town. One of these famously was found that gave us this idea of eye for an eye, because they were actually meting out consequences for if you broke these laws, right? So the laws appear. They almost seem to predate anyone having written them down. There's this huge argument in after the Enlightenment, where people are trying to actually, like these guys like Hobbes and Locke are sitting around arguing about where the heck do we get, who gives us the right to put laws down? And the argument that's often made is that laws are naturally occurring, essentially. These things are self-evident, because if you didn't have the law that you can't steal from people, well, you wouldn't be able to form trust with people, and you wouldn't be able to actually have a civilization in the first place. Likewise, murdering people, it doesn't work out, right? If you can just murder someone because you disagree with them, well, you're never going to be able to actually work anything out or actually collaborate on anything, because you're going to be too afraid about getting murdered at any given point in time. So religion, in its earliest sense, actually arises out of the need to codify these laws that in some sense are cosmically apparent, right? These laws are sort of there, and people write them down and they celebrate them in the stories that they tell. Now, I'm going to leave you with this. There have been some interesting attempts to get rid of religion especially in modern times, right? So Nietzsche, who's come up a few times in this course, had this idea that, well, humans have become so rational recently that they just can't tolerate these superstitious stories anymore. They can't believe there's a guy with a beard in the sky who's pulling all the strings. It's just, they were not buying it, right? We have mechanistic models for electricity and magnetism. No one's buying this stuff anymore. And at some point in the near future, religion's going to be completely pointless. People are going to have to come up with their own individualized frameworks for grasping the cosmos, right? Now, this guy, Karl Marx, took that very seriously, right? And he actually thought, well, religion is just this, way that the power structures, let's say the power elite, keep the masses down. He called religion the opiate of the masses. And actually, Marx built this entire worldview based on the idea that the entire world functions as the result of this giant power struggle. Now, there's some truth to that. Certainly there's a lot of power struggles going on in the world, and you've probably encountered a few of them in your life. But they're kind of a drag, right? Like, I imagine when you're hanging out with your wife, your significant other or your best friends, how many times an hour are you thinking about how much power you have over them or they have over you? Almost never, right? I'm telling you, your marriage will last 5 minutes if this is how you approach it, right? I don't agree with him that this is the fundamental motivational structure for humanity. I think that there's a much deeper spirit of togetherness and collaboration that actually drives things much more than power dynamics do, although that can be a very pernicious flavor of things that appear from time to time. The problem is people tried this, people have tried to get rid of religion and it just won't go away is the thing, The last thing I'll leave you with is there's an experiment, right? So an entire country, several countries in the back half of the 20th century tried on Marx's idea of eradicating religion and setting up these communist utopias. And those were complete disasters, right? So what happened? Well, what's the worst thing that you can call somebody in today's society? Probably a Nazi, right? Well, the Nazis, they exterminated something like 6 million people that they didn't like, mostly political dissidents, people whose religion they didn't like, right? The Jewish people, transients. They killed a lot of people, and it's obviously a complete horrific tragedy. The Soviets killed 60 million people. They exterminated 60 million people under this doctrine of being able to homogenize people and get rid of this cosmic ladder, right? That Marx envisioned that people would get rid of. And so that experiment didn't work at all, right? That was a complete nightmare. So what I'm trying to work towards here is that in modern astronomy, and we'll pick up with this next time, we have done everything we can to get the mystical out of our science, right? We're trying to be extremely objective, we're looking at the data, we're interpreting it. But are we capable of truly interpreting something outside of our own lived experience? Can we look at the universe inside, from behind eyes that have a birth and a death, without seeing a birth and a death inside of the entire universe itself, right? Can we actually do it? And if we can't do it, then shouldn't we at least be cognizant of it and actually maybe take some time to celebrate these processes as well? So next time I want to tell one particular myth to really just seal this deal for you about how important and persistent these ideas are and how relevant they still are to our modern lives. And then I want you to, again, I want you to reconsider whether we're actually capable of being completely objective in our analysis of the stars, even to this day. So think about the Sumerians over the weekend. I want to hear your ideas of why in the heck they were using a base 6 system. Try not to Google it. I want to hear your ideas. And have a great weekend, guys. I will see you all Tuesday.